Sure, sure, sure.
Thank you, ma'am.
So lab classes will be for 2 hours duration. So during the lab course, a recorded video on the respective experiments will be played, after which we will, both of us will discuss or will conduct a discussion session on the lab. So the students are required to keep the printed manual. If you have carried back with you the printed manual, please use that printed manual. Or if you cannot print it out, we prefer that you print it out, you print out the manual and keep the hard copy ready with you. But in case due to the prevailing conditions, prevailing lockdown situation and all, if you are not able to have a hard copy with you, you can bring or you can use the soft copy for reference. And in case if you're using the soft copy, you're supposed to write down everything manually in the paper while submitting your assignments. Okay, so the observation data as well as viva questions for each experiments of given lab class will be provided in the assignment tab of MS Team. So here also today, for today's class also, we have created one assignment and it is uploaded in the assignment tab of MS Team. The write-up mandatorily should be handwritten and it should be uploaded in the assignment tab containing the following: student name, register number, roll number and signature on every page. Okay, so entry in the observation table along with specimen calculation showing clear substitution of values should be there. Okay, you have to write the observation properly. You have to write the required formulas, do proper substitution and then show your final answers along with units. Okay, if someone has missed their units, they are bound to lose marks. There should be clear results and conclusion. Graph sheets, if any, should be attached. Okay, and we also require a line diagram of the setup with complete labeling. You can see the setup while when we are playing the video. You can see the actual lab setup also. At the same time, the setup diagram is also provided in the manual. You can use that, but we want a line diagram with complete labeling. It also carries marks. Finally, you have to answer the viva questions. Okay, so all this write-up should be scanned as a single PDF document. You have to arrange the sheets in proper sequence for 2 experiments. You will be conducting 2 experiments in each lab. So you arrange the sheets in proper sequence for both the experiments before scanning. Please write page number at the top of every sheet. The file should be named as batch number underscore roll number underscore experiment number. Okay, say for example, if batch is A1 underscore roll number is 21 underscore experiment 1 underscore experiment 2. Okay, you will be conducting then. Similarly, for the next class, it will be experiment 3 and experiment 4. Okay, right? So the uploading of your worksheet must be completed before tomorrow's midnight. Midnight in the sense 11:59, not 12. Okay, 11:59 will be 11:59 PM is tomorrow. 11:59 PM is the last deadline for you to upload your sheets. Clear? Anybody is having any doubt here?
Ma'am, we write this in the physical manual if we have it and then scan it.
If you are having but then you have to show all the specimen calculation. You have to write your fill out your observation table and you can do it. If you are having your manual with you.
Madam,
Yes.
let them write on a paper and then scan.
Okay. Okay, sir. Done. Please do write it on the paper and scan. We will maintain a uniformity. That will be better. Any other doubts? This PDF file is uploaded in the files tab. You can revert back to this file whenever you want and you can go through the instructions once again. Done? No doubts, I guess. Nakul sir, can you play the video?
Yes, ma'am. Okay. So you just unshare. I'll start.
Yeah, I'll do it. I'll do it.
All of you can hear?
No, sir.
Nakul, while up,
No, sir, we
Nakul, you
can't hear.
just have to turn on the system audio. Unshare it now. Okay, so while sharing, once you click the sharing button there, you have system include system audio. It should be turned on.
Can you hear?
Yes.
So I'll start from the beginning.
What you see here is a spherical disc. Inside this there are powders of asbestos. It is regarded as
So your screen is stuck. Only the audio is going on.
Screen is stuck, is it?
The screen is at 17 seconds, I think.
Now it is stuck. Now I have paused it.
insulation that used to avoid heat losses to the surroundings from a given body. In this experiment, we're trying to
So it's stuck at 17 seconds.
there are applications where it's not regular.
Now everybody is having the problem, or only you are having the problem? Please
No, sir,
respond,
it's
guys.
win for me, sir. So
Sir, we also have the problem.
I'm able to view the video, sir. Like explain.
This is actually an MS Teams problems. Videos don't play properly.
Okay,
You
so
might
what
have to send us the recording.
Now that what you do is now anyway the video will be played and it is being recorded. No, the meeting is being recorded. So in that recorded video, you can see the video properly.
No, sir. Even in the recording, the video is going to be stuck again and again. You'll have to send us the video itself.
Okay. So that we'll just communicate with the coordinator, and if it is possible, I'll just send you the link one by one before afternoon. Okay, if it is possible.
Okay,
If it
sir.
is not, you guys have to manage with this. So just pay attention, and then we'll see what can be done by afternoon. If it is possible, I'll send the links.
So could you play from the beginning?
Yeah.
Nakul, can I try it from my side once?
Yes, ma'am. Yes, yes.
Just. Can everybody see my screen? No?
Yes, ma'am.
This experimental setup is to determine the thermoconductivity of insulating powders. What you see here is a spherical disc.
Please confirm whether it's audible properly.
Yes, ma'am.
Inside this powders of asbestos, which is regarded as an insulating powder or insulating material. We use insulation materials to avoid heat losses to the surroundings from a given body. In this experiment, we are trying to see how good asbestos is as insulating
Excuse me, ma'am.
material.
Ma'am,
There are applications where we
ma'am, it's getting stuck again and again.
Yeah, right. See, it requires bandwidth at your side also. Right. Ensure that you sit in a place where you have good connectivity.
Yes,
Few
ma'am.
might, few might be having this problem because it's their internet connectivity problem. It requires bandwidth, right? So please bear with it, go through it. Those who are facing the problem, the meeting is recorded. Later on, you can go through it, and we will also discuss the problem with the coordinator. And if possible, we will send you the recordings. Okay?
Okay, ma'am.
It's not regular, it's not always that we use a rectangular form of asbestos sheet. There are applications where you may have to give a particular shape, maybe spherical, maybe hemispherical, or maybe any other complicated shapes as well. To demonstrate this aspect, we are using a spherical shape here where we insulate the heat loss by using powders of asbestos. That's why we are making use of a spherical shape here to specifically demonstrate its capacity, its ability to avoid heat in its powder form. The other aspect here is when we make use of powders, we can fill it into any shape. It doesn't have to be in a particular form, may not be a rectangular shape. It can be in powder. Once it's in powder form, we can fill the powders into any shape. So it can take the shape of the container. So both aspects have been highlighted in this experimental setup. What we try to do is, we need to determine the thermal conductivity of the insulating powder. So the moment I say thermal conductivity, we are talking about conduction heat transfer. So I can take up the Fourier's law of heat conduction basic expression, apply it to the coordinates of sphere or spherical coordinates, and we have a fundamental equation wherein in order to find the heat transfer by conduction in a spherical coordinate in one dimension, I'm talking about a one dimensional heat transfer, all I need is the thickness of the insulation, that is the difference between the outer radius and the inner radius of the insulation, as well as thermal conductivity and the temperature difference across which heat transfer takes place. So these are the three key parameters. But in this experiment, the objective is to find out the thermal conductivity K. So that is the unknown thing. So what is that we know then? We know the thickness of the insulation because we have a geometry here. I can measure, it's already measured and the data is known. We know the inner radius and outer radius of the insulation. So we know the thickness of the insulation. We also know the amount of heat transfer that is taking place because it is us, we are providing the heat input. The water heat input we provide using a thermostat here, using electrical heating, V into I is the electrical heat input, that should be released to the surroundings. So we know the heat input Q, we know the difference between the radius which gives us roughly the thickness. So all you need to know is the temperature difference. That is, the temperature difference delta T across which the given heat input is making its flow. But where do we find the temperature difference here? Let's understand the setup to understand that better. What we have here is a sphere. It is hollow on its inside. So it is hollow on its inside. There are two spheres, two hollow spheres rather. The inner sphere is heated electrically, and in between the annulus region of these two spheres there are powders which are packed. So you have two spheres, one inside the other, and the gap between two spheres is what is insulated using insulation powders. The inner surface of the inner cylinder, sphere, the inner surface of the inner sphere is electrically heated using electrical coils, and therefore the heat tries to make its flow from the inside of the sphere to the outside of the sphere, because the outside of the sphere is exposed to the atmosphere. This is a heat sink. The atmosphere is a heat sink. So there is heat conduction across the thickness of the insulating powder. We are providing a known heat input and allowing the heat conduction to take place, and we know the thickness of the insulation, but we do not know the temperature difference across which the heat conduction is taking place. So the objective of this experimental setup, though, is to determine the thermal conductivity of insulating powder, which is the ultimate objective, but the immediate objective of doing the experiment here is to know the temperatures on the outer surface of the cylinder as well as on the inner surface of the sphere. I'm sorry, correct it as sphere, not cylinder. outer surface of the sphere as well as inner surface of the sphere. So that is why you are doing the experiment. If these temperatures were known somehow, we didn't have to conduct experiment at all. We don't need an experimental setup at all. So that's the difficulty. We have to conduct an experiment to know the temperature distribution on the outer surface as well as on the hot and inner surface. And we provide a known heat input. We have thermocouples, 3 thermocouples set on the outer surface. You can clearly see here there are 3 screws we could see. Similarly, there are 3 more thermocouples on the inner side. We allow the heat input, a known heat input. We can determine the heat input by the product of voltage and current. Once you know the amount of heat input that has been supplied, allow the steady state to reach. In all heat transfer experiments, we are taking the readings at steady state conditions, which means the temperatures are no longer varying over time. So we allow the setup to reach a steady state for about half an hour or 20 minutes as the case may be. And once a steady state is reached, you are going to note down the readings. This applies to all the experiments in the heat transfer lab. We will have to note down the readings at steady state conditions only. Now, there are temperature recordings here which can be noted down. There are 6 readings. You will be able to note down those readings. Supply these values of temperature into the fundamental equation of Fourier's law. You will be able to find out the unknown thermal conductivity of the insulating material, that is the asbestos powder. We should be able to find out that the thermal conductivity of this powder will be very low. Because we are talking about asbestos, which is insulating material, it must have a very low value of thermal conductivity. That must be clearly noted. And you can repeat the experiment for different heat inputs and then take an average value of K or thermal conductivity. But different trials can be taken up, or maybe one trial itself is enough. That's it from this experiment.
Okay, so this was about insulating powder. I will be playing the second video for second experiment today. Can everybody see the screen?
Yes, ma'am.
Hello students, you can see the experimental setup here for measuring the
Just to confirm, can you hear the audio?
yes ma'am. The thermal conductivity of metal rod. So in the setup you can see heating section here and the test section and then cooling section on the other side here. So you can see the specifications of the test setup. Okay, we have a metal rod of 400 millimeter long and its diameter is 20 millimeter. And the material of that rod is aluminum, and you can see the setup. The rod is kept in the center and it is well insulated. A very thick insulation is provided so that we have a one-dimensional heat transfer. So our aim is to find the thermal conductivity of that metal rod. So you know from the heat transfer course, the law that governs the heat conduction is Fourier law, and the rate of heat transfer is directly proportional to temperature gradient along the surface rod. So we can take planar wall or a rod or a material metal where we have to make the heat transfer along one direction, and then if we know the temperature gradient and we know the area of cross section through which heat flows, if you can measure the rate of heat transfer, through that we can measure the thermal conductivity. So here, the setup, you can see we have a heating section where we supply the heat energy using an electric heater, and amount of heat energy supplied to the heater is taken down from this voltmeter and ammeter, approximately 50 watts, okay, 100 volts, and this is 0.5 amps with supply, and then we have to wait for sufficient time to attain the steady state. Okay, this is a steady state experiment, and along the rod we have a temperature gradient. Okay, temperature will be very high at this end, heater end, and the temperature is low at the cooling end. So heat transfer, when it attains steady state, we know that by noting the temperature along the rod. So we have 5 locations to measure the temperature on the surface of the rod. So we have T1 to T5. They will give the temperature of the rod along X. So the distance between each point, measurement point, is 70 millimeter. And we also have 2 more thermocouples to measure the inlet water temperature and exit water temperature in the cooling section. So by knowing the mass flow rate of water using the rotameter, we can know the flow rate, and we know the density of water, so we know mass flow rate. Cp of water we know, so we can write, we can obtain the rate of heat taken by the cooling water. So we know what is the heat conductive to the rod from inlet temperature of water and exit temperature, and the mass flow rate of water and Cp we know, that means we know the rate of heat conducted to the rod. So that heat is actually coming through the conduction along the rod, because the radial heat transfer or the peripheral heat transfer is prevented by providing a good amount of insulation there. So we have to make this 1D heat conduction assumption here, and so we can plot the temperature versus distance graph, and from that graph we can obtain dt by dx. Okay, so fit a straight line to the data, you obtain temperature versus x data and obtain dt by dx, and then use that to calculate the thermal conductivity. So by equating the conduction through the rod, because we know the cross section, so we can find the area, and we know dt by dx from the graph. So only unknown here is thermal conductivity, Ka dt by dx equal to the amount of heat that is taken out by the cooling water here. So we know the mass flow rate, we can measure that using the rotameter. Inlet temperature, exit temperature of the water, we can measure using the thermocouple, that is T6 and T7. And then we know Cp for the water, so we know the amount of heat taken by the cooling water here at steady state. And so we can calculate the thermal conductivity for the metal rod.
Okay, so we have gone through the video of the 2 experiments. One is insulating powder, and second one is the thermal conductivity of metal bar. So we will start with a PPT just to brush through what you need to do in the respective experiment. So we'll start with the first experiment. It is to determine thermal conductivity of insulating powder. Please confirm whether I'm audible.
Yes, ma'am.
You can
Yes,
see
ma'am.
the screen. You can see the screen.
Yes, ma'am.
Okay, so thermal conductivity. So what is thermal conductivity? Thermal conductivity is a property of the material and may be defined as the amount of heat conducted per unit time across unit area and through unit thickness when a temperature difference of unit degree is maintained across the bounding surface. So we are going to use the Fourier's law of heat conduction to find out the thermal conductivity. So what is Fourier's law? What does Fourier's law state? Fourier's law of heat conduction states that the rate of heat transfer through a material is directly proportional to the area normal to the direction of heat flow and the temperature gradient. So from the Fourier's law of heat conduction, we have the following equation. Q equal to Ka product of the temperature gradient. Okay, so where Q is rate of heat conducted, A is area of heat transfer surface, K is thermal conductivity of the material, and dt by dx will be the temperature gradient. This is the setup, experimental setup, and we want you to draw the line diagram of the setup. This is how internally the thermocouples are arranged. This is your inner copper sphere. This is your outer copper sphere, and T1, T2, T3, T4 are the thermocouples mounted on the inner sphere, whereas T5 to T10 are the thermocouples which are mounted on the outer copper sphere. So we'll start with the Fourier's equation. Q equal to Ka minus dt by dr. Dr is, the reason is here we have a spherical cross section, that's why r radius comes into picture. Area 4 pi r square, area of the sphere, that is what you are going to substitute. Here you want to find K. Okay, so then you will proceed with the integration, and then finally you will get Q as 4 pi K R naught Ri, where R naught represents the radius of the outer and outer sphere, Ri represents the radius of inner sphere. From the previous equation, you will get your K, and you are going to finally end up with a value of K, thermal conductivity. What is the thermal conductivity? Now here in this setup, you are using asbestos as the insulating powder. Your K should be high or low?
Low.
Thermal conductivity, should it be high or low?
Low.
You know that
Low.
it varies low. Why? Because asbestos in itself is an insulating material, right? So that should be your inference. If you get a high value of K, what will be your inference?
Then it's not a good insulator. It's a good.
It's a conductor, yeah.
Then yes, but the material property is of course insulating. It cannot be a conducting powder. You cannot give a statement that asbestos is a bad insulating powder or material. You cannot give that statement. There you have to find out where the error is arising out in the experimental setup. Where can you get the errors here in the experimental setup? If you see the equation here, my area, my radius and all will not vary. They remain same. Okay, only my temperature varies. So what is giving me the temperature reading here in the experimental setup? These are my thermocouples. So there might be error in the readings obtained by the thermocouples. So either you need to replace the thermocouples here. So that should be your inference. You cannot give a statement that asbestos is a conducting material. You cannot do that. Understood? Clear?
Yes, ma'am.
Yes, ma'am.
Okay. Right? How are we going to conduct the experiment? We'll connect the equipment to electric power supply first. Keep the thermocouple selector switch to 0 position initially. We have to turn the thermostat knob clockwise and adjust the power input to the heater to the desired value. Say a voltmeter reading of 125 volts is selected here. So thermocouple readings are taken by operating the selector switch when steady state has been reached. You have to repeat the experiment for different power input to the heater. Finally, switch off the power supply. This will be your observation table. Volts, current, ampere, you will write down. Then you will note down the thermocouple readings. So T1 to T10. Okay. Inner radius of the sphere will be 50 mm. Outer radius of the sphere here in this setup is 100 mm. You have to first find the average inner surface temperature. Also find the average outer surface temperature to get our Ti and T0. So we have this equation for finding the thermal conductivity of insulating powder, which has been derived by the Fourier's law. So using that equation, R0 is known, Ri is known, Ti and T0 are measured. Then you will find the thermal conductivity. Q also is known. You will be noting it down in the observation table. Finally, you will find the thermal conductivity of insulating powder. Any
Ma'am,
doubts here?
Ri and R0 are 50 and 100.
Yeah. Yes, they are fixed. Setup.
That is for the outer sphere or the inner sphere?
See, R0 is for outer sphere. Ri is inner sphere.
Okay, ma'am.
Clear here? R0 is outer radius of the sphere. Ri is inner radius of the sphere. Okay, fine. So I will be sharing everybody, can you see my screen?
Yes, ma'am.
Yes, madam, you continue. No problem.
Okay. So the aim of the second experiment is to determine the thermal conductivity of aluminium rod. Again, we have discussed what is thermal conductivity. So it is a property of the material and it may be defined as the amount of heat conducted per unit time across unit area and through unit thickness when a temperature difference of unit degree is maintained across the bounding surface. Again, we are going to use the Fourier's law of heat conduction. So this is the equation that we have from Fourier's law of heat conduction. This is the experimental setup. And once again, I'm repeating, students are required to draw a line diagram of the experimental setup. This is how, again, I'm telling you once again, many of the students write this sketch. This is not experimental setup. This is to show how the thermocouples are arranged inside or on the metal bar which is placed inside the setup. So this is not the setup sketch. Please don't write this sketch and expect marks.
Ma'am, could you actually go back to the setup sketch and tell us what the part is, because it wasn't very clear in the video.
You see it once again. It's recorded. It's available. You just go through the recording. I want everybody to go through the recording once again before starting your actual write-up, because it is very, very important. You can't remember everything right now. Once again, you go back to that recorded video. Once again, play that video. Just go through everything. Okay. This is the,
Okay, ma'am.
I will just tell you, here inside is your metal rod. This is your rotameter. Okay. These are the thermocouple readings where you are going to get. This is the knob by which you can select the thermocouple. Okay. So T1 to T7 are the thermocouples here, right? Assuming the bar is properly insulated and there is no heat loss, we know that heat conducted through the rod will be equal to heat carried away by the cooling water. Okay. So heat conducted through the rod can be written as minus Ka dt by dx. Heat carried away by the cooling water is mcp delta T. So mass flow rate of water, Cp of water, the thermocouples that are there to measure the cooling water heat transfer. So T7 and T6. If we rearrange the terms here, then we can obtain K by using this equation. So rearranging the terms properly, we will find the thermal conductivity of the rod. What is the thermal conductivity of aluminium? What should be the thermal conductivity of aluminium? We should end up with what value?
It should be high.
High, I know. There's a number. I know that this is aluminium. How much? 200, 210, around that value you have to have your thermal conductivity value for aluminium. Okay. Right. So in the equation, dt by dx is the temperature gradient in degree Celsius per meter, area of the metal rod pi d square by 4, where d is diameter of the metal bar, Cp of water, specific heat of water, 4.187 kilojoule per kg Kelvin or 4187 joule per kg Kelvin. M is the mass flow rate of water. So the mass flow rate of water is found by density of water multiplied by QW kg per second. Okay. Volumetric flow rate is what you are going to find from the experimental setup. You know the density of water, which is a standard. So using these two values, you will get the mass flow rate of water. Procedure, you have to connect the equipment to the electric power supply. Give heat input to the heater by slowly rotating the dimmer stat and adjust the voltage. Set the cooling water supply through rotameter, say 0.2 liters per minute LPM. So allow sufficient time to reach steady state. Note down the temperature at different length and also rise in temperature of jacket cooling water. Repeat the experiment for other heat input. Okay. Switch off the power supply. Observation, what you are going to note down is this. So this is the table, observation table. Voltmeter reading you will write, ammeter reading you will write. Then multiplying these two, you will find out the heat input. All the thermocouple readings and the volumetric flow rate of water. So these are the observations that you will make near your experimental setup. Okay. In order to plot the graph to get the temperature gradient, you need to know the distance between each thermocouple. So this is how the thermocouples are arranged. The distance between the thermocouples is 70 mm. So first thermocouple will be at 70 mm. Second thermocouple 70 plus 70, it is 140, like that. Okay. Only 5 thermocouples are there on the metal rod. Okay. 6 and 7 are there for measuring the heat transfer. Heat transfer through the cooling water. So you don't plot 6 and 7 also in the graph. It should be 1 to 5. Draw the variation of temperature along the length of the bar to obtain your temperature gradient. Take a proper slope to get dt by dx. Area of metal rod you have to calculate. Then find out mass flow rate of water. Substitute the values in the equation to get your K. Any doubts? So in these two experiments, the graph is there for the second experiment. You're supposed to plot the graph here to get your temperature gradient dt by dx. Any doubts? Anybody's having any doubt here?
No, ma'am.
And Nakul, is there anything else to deliberate?
Nothing, madam. Last is that assignment stuff. It is posted in your assignment tab. It will be, assignment should be on by now. I gave the time as 10:30, so it should be already posted by now.
Okay, so the readings are provided there. If you just go through that assignment sheet in the observation table. Yes.
And also the Viva questions are also given in that same file which is attached.
Yes.
That's it, and you should submit it before tomorrow midnight. Okay, that is the deadline.
And please stick to the deadline, because sticking to the deadline will ensure maximum marks. Those who take the time beyond that, stating might be n number of reasons, we are going to reduce the marks for late submission. You have been given sufficient amount of time to do your calculation. Please do stick to the strict time frame. Any doubts? If you don't have any doubt, we can leave or end the meeting. Yes, Nakul, anything else?
Ma'am, can you please tell once again what all do we have to write?
See, it is there is a file which is uploaded in the files tab, instruction to students. You just open that, and everything what needs to be done is properly given there point by point. Okay, go through it and follow the procedure. Clear?
Yes, ma'am.